privilege today to actually invite Professor Wendy Tan Ao, and she's also have a very interdisciplinary background. She is a professor in the Department of Political Science, Statistics, Mathematics, Computer Science, Asian American Studies, and the College of Law. She's also a senior research scientist at the National Center for Supercomputing Applications, faculty in the Illinois Informatics Institute, and affiliate of the Klein Center for Advanced Social Research, the Computational Science and Engineering Program, and the Program on Law, Behavior and Social Science at the University of Illinois at Urbana-Champaign. She has also been awarded fellowship by the John Simon Guggenheim Memorial Foundation, the Society for the Political Methodologies, and the Hoover Institute, as well as the Center for Advanced Study in the Behavior Science at Stanford University. She has a series of publications in a very wide range of journals, all very top journals, including Nature and Science. So, may I invite you to join me to welcome Professor Wendy Ao to present the topic, AI in Democratic Governance.
So this is my talk, The Role of AI in Democratic Governance. This is a long project of mine, about 8 years worth of work now. And it spans work in lots of different disciplines: computer science, physics, statistics, mathematics, law, political science. So I'll talk about a little bit about each of those things today, and I'll explain the basic application to you first. So this is a picture of how redistricting is done in the United States. So if you look at this map, we're going to start with this one. The idea is we have a set of voters. Some of them are Republican and some of them are Democrat. And what we want to do is put them into districts. So they will vote within a district. And there are lots of ways to do that. So we're going to put them into 4 districts. So in the United States, when you put people into districts, you have to put the same number of people into each district. All right. So we can make the districts like this. This is a district. So those 3 people are in a district, and that district will vote Republican because they're all Republicans. This district is another one. It also has 3. And this district will vote for a Democrat because there's 2 Democrats and 1 Republican. This one is a district, and this will elect 2 Democrats and 1 Republican, and this one also. So there's still half Republican and half Democrats. I haven't even moved them. See, here are the Republicans. They're still here. Here are the Democrats. They're still here. But after I put them into districts, I have 25% Republican and 75% Democrat in the legislature. So notice here, I again have not moved anyone. The Republicans are still here. The Democrats are still there, just like there, just like there. But now I create this district, and this district is going to elect a Republican. This one is going to elect a Republican. This one is going to elect a Republican. And this one will elect a Democrat. So now nobody has moved. Nobody changed their vote. But now I have 75% Republican in the legislature and 25% Democrat. I can also separate them this way so that I have this as a district and those are Republicans. This one will also vote Republican. This one will vote Democrat, and this one will vote Democrat. And so I still have in all these instances half Republican, half Democrat because nobody has moved or changed their vote. But now I have half Republican and half Democrat. So it doesn't matter what the voters do. The voters always do the same thing, as you can see. The only thing that changes is I put them into districts in a different way. And that determines the entire outcome. So this is interesting because even though the United States is a democracy and everybody votes freely, and everybody can go to the polls, nobody is prevented from going to the polls, all the votes are counted. We don't throw away votes. Unlike maybe some of the news stories you've heard, we didn't throw away votes, at least a lot of them. All the votes are counted, but the outcome itself can still be manipulated, and very heavily so. So this is the idea behind redistricting, is every 10 years in the United States, we redraw the maps for every state. So we're just turning into 2020 where we will redraw the maps again. And this has been a big issue. So this is a picture of House reelection rates in the United States over about 40 years. And as you can see, there's 435 members of Congress in the United States. So every 2 years, all 435 members of Congress are up for re-election. So all 435 every 2 years. And as you can see, we re-elect them at these extremely high rates. The average is in the mid-90s. So almost all of them are re-elected all the time. However, we don't like Congress. If you ask the US, do you like Congress? Do they do a good job? Universally, we say no. They're no good. But yet we re-elect them at these high rates. And so one of the reasons people think this happens is in part this idea behind redistricting, that you draw these maps and the districts that they run in, they're very safe. So they're not going to get unelected. And Republicans generally, they always vote for Republicans. Democrats vote for Democrats. So that's the idea. And what people don't want is this situation where you draw the maps so that they are very skewed toward one party. In most of the US, the way it works is every state gets to decide how they will draw the maps for their own state. And usually they pass it as a regular law. So the legislature will draw the map and they will pass it as a law. So whichever party has the majority, usually will draw it in their favor, because all they need is to pass it with a majority vote. So this is something that has been going on for a long time and people want to somehow fix. So I'm going to show you some districts. This is the state of North Carolina in the United States. And this is a picture of its districts in the 1990s. So this district, the 12th one, has always been a fun one for us. It's been litigated many times. And as you can see, what kind of shape is that? Right? It's actually 160 miles long, and most of it travels along. This shape is the shape of a freeway in North Carolina. And what happens is, let me go to my laptop again, they're trying to get people in their district. So they get some people here, and then they decide to get on the freeway. Then they get off the freeway, and they get some people, and they get back on the freeway. Then they get some people here, and they get back on the freeway. Oh, here's some people back on the freeway. So they have to travel all the way down this freeway to get enough people for this district. And in fact, this district is so thin in some places that if you get off the freeway and get back on the other way, you're in a different district. So it's very carefully drawn. This is the 4th district in Louisiana. I don't know if you know what Louisiana looks like, but it basically looks like this. So this is the shape. The whole state, the top, the side, the bottom, is all in one district. And it's not very close to each other. This is from my home state of Illinois. We like to call this the earmuff district. You put those on your ears, the earmuff district. If you put this over an actual map of the district, what you can see is this area has lots of people, that area has lots of people, but to the left of this area, there are no people. This is a freeway, this is a railroad, this is a forest preserve, this is a cemetery. So no people, no live people over here to vote. All the people who are alive are over here. This piece is just a connector to connect those two pieces. So you can see we can do a lot with our drawing. We're very creative in the United States. This one, I always say, is my favorite district of all time. This is my personal favorite because it's so artistic. Do you see the horse? Yeah, the horse is sitting up and there's like a cow falling off the horse. So I always like to say, sometimes I tell you there are ugly districts, and if I gave you a piece of paper and you all sat down and I said, let's draw ugly districts, so you're not this good. This is so much better than anything you could do. Like you would go, oh, how about this? Is that ugly? It's not ugly. This is masterful. This one I like because it looks like a dog. Although I've given this talk before and someone told me it's a lobster. And for a long time I couldn't see the lobster, and then I finally saw the lobster. This is the lobster tail. But I always thought it looked like a dog. This looks like a dog, right? It's a dog. It's a dog. So here's another fun thing we like to do in the United States. We like to give our districts names. This one's the hanging claw. This one's the pinwheel of death. So this one's a little bit funny because it's actually not connected here, but there's a requirement that districts have to be connected everywhere. So it turns out you can connect underwater. So this is connected underwater, so it is technically connected. This one was litigated a couple years ago in 2018. And then when the media saw this district, they decided they were going to have a contest to name it because they didn't know what to call it. And so they had a contest, and the winner was Goofy kicking Donald Duck. Here you can see Goofy, and Goofy is kicking Donald Duck. So these are actual districts. I didn't draw any of these myself. I'm also not this good. I could never draw something quite this good. I mean, that really looks like Goofy. So, I'm not that good either. So those are actual maps. And then what happens is people see these maps, they see these districts, and they say, what are you doing? Why are we drawing this kind of shape? What is going on here? And are you making it so that like the Democrats get elected more than they should? Or the Republicans are being elected more than they should? And this phenomenon is called partisan gerrymandering. So in the United States, partisan gerrymandering, where you draw the districts to favor your own party, it's unconstitutional, right? You can't do that. The problem is, we don't know what that means. So the definition is you can use partisan information, but you can't use it excessively. That's actually a legal definition. So in the United States, if you use it excessively, then it's struck down by the court and it has to be drawn again. If you use it but don't use it excessively, it's okay. So like, okay, that's the definition that the court uses. So the way I like to explain this is I like to show the apple, because we can all look at the apple and we can all agree, is that an apple? Yeah. Yes, it's an apple. So now the harder question, is it an excessively red apple? And they're like, it's like the maps. Is this a map? Is it an election map? Yes. Is it excessively partisan? It's the same thing, right? So you're looking at the apple and I ask you, is it an excessively red apple? And you're like, I don't know if it's an excessively red apple. How would I know if it's excessively red? Because if it's excessively red or excessively partisan, then it has to be redrawn. But if it's not excessive, but it's red or it's partisan, it's okay. So the way I like to explain this is if you want to measure excessiveness, what you want, like for the apple, is to find all the apples. And then you line them up in order of redness. Right? So on one end, you have the green apples, and then it turns into the yellow apples, and then there's some pink apples, and then there's red apples, and then there's really red apples, right? And you want to know this apple, where is it in the line? So basically, you got to go shopping for the apples, and you got to go find them, right? Because you want to know what they look like. Do they look like this? Do they look like that? Are all the apples red? Are they green? This is a picture from Taiwan. You have lots of apples. I don't see many green apples, by the way. I don't know why. So the idea is if you have a map or an apple, and you can find all the other apples, and your apple or your map is like over here, then you can say, oh, that's excessively red, or it's excessively partisan. This is how you would create a test to determine something like that. On the other hand, if you have, this is the same map in the exact same place on the line. If you found all the other apples or all the other maps and they look like that, then a judge could look at that and say, okay, no, that's just like all the other maps. Okay? So this is what actually happens in court. There's a map that people are suing about, and the Democrats come in, and I don't know where the Democrats go shopping, but they found all the green apples. And they couldn't find any red apples. And they come into court with this big basket of green apples, and they say, look at that apple. That's the reddest apple ever, because all the other apples are green. this is actually what they do. And then the Republicans come in, and I don't know where they shop either, but they went to the super red apple store, and they got a big basket of super red apples, and they come into court saying, that apple's not red at all. Look at these apples, right? And so the problem is, you know, are either of these the distribution for all the apples? So, you know, this is the problem. The Democrats bring in this basket, and the Republicans bring in that basket, right? And the judge says, did anyone go get all the apples, or did you guys just go shopping at your special apple store, right? And so this is a problem for the court, because if you look at this problem, sorry, this is how I formulated it. It's an application of what we call a graph partitioning problem, which is NP-hard. So if you're a computer scientist, you know what that means. And if you're not a computer scientist, you can just replace NP-hard with really, really hard. That's what NP means. It's a really hard problem. And the total number of possible maps that you can draw is really, really large, is very, very big. So if you were to take, if you had 55 things and you were to put them into six districts, and there were no constraints on how you were to do that, there's 10 to the 39th ways to do that. So that's a really, really big number. So to give you some idea about how big that is, there have been fewer than 10 to the 18th seconds since the universe began. So this is much bigger than the number of seconds since the universe began. That's how many ways there are. And this is 55 units into 6 districts. So in a real redistricting application, this is the state of Minnesota. There are, you want 8 congressional districts. So you want to take the state and put it into 8 districts. There are 4,000 precincts and 250,000 census blocks. So this is a picture of the census blocks. And we have data at the census block level in the United States. So you can see, if these are my little blocks, and I just have to put them into sets of 8, there's a lot of ways to do that, right? A lot. So you can draw your, you know, Goofy kicking Daffy over here. You can draw your other district that goes all along the state over here. You can do whatever you want, because you can do anything, right? Because those are your building blocks, and you want to put them into 8 congressional districts. So now, you know, you go to the judge, and you know, what are you supposed to say, right? Because there's so many ways to do this, and in order for it to be overturned in a court of law, you have to convince the judge that this map, the one that was actually drawn, is excessively partisan. But the set of maps that can be drawn is so massively large. So if you wanted to compute that, it's, like I said, it's really hard, right? It's really hard to figure out how to do that. And even though everybody looks at the maps and they think, oh, of course the Democrats were doing that, or of course the Republicans were doing that, that's a different question than, can you prove it in a court of law, right? Can you produce an actual test that will be fair for everyone, that we can use all the time, and that we can always say, we use this test tells us this map is excessively partisan. Because right now we didn't have a test like that. And people just do what I said. They bring in their own, you know, basket of apples, their special basket that they got somewhere. And nobody knows where did you get those apples? You know, did you actually try to shop for all the apples, or you know, and of course they never try to shop for all the apples, because that's not what they do. So this is something that we were trying to do with our algorithm. So the basic idea is, I actually didn't have this idea at the beginning. This idea evolved as the court evolved. But my first idea was, can you teach a computer to draw a map? Like, just have a computer draw a map. And it turns out that's not that easy. But this was the first step of the project, was, you know, can I teach a computer to draw a map? So we started with this idea, we would just randomly create a map. So the problem with randomly creating a map, so now Minnesota is separated into 8 districts. The problem with that is, this is not what we would call a legal map. So in the United States, there's all sorts of criteria for a legal map. So one of them I already told you, same number of people in each district, right? And if you just randomly put things into units, that doesn't happen, right? It just doesn't happen at random. But we have other constraints too, like this contiguous constraint. Everything has to be connected. They like it when you preserve cities and counties so that there's, some way to, think of this as a reasonable way to group people. We have a thing called the Voting Rights Act, which preserves voting rights for minorities. So there are all sorts of laws that have to be fulfilled when you create a map. So if you just create one at random, it doesn't happen, right? It doesn't just happen. And so the thing we had to do with the computer basically was to say, okay, I'm going to start with this random map. And then what I'm going to do is, or you, the computer, computer's like my friend, I talk to it. What you computer, you will do is make it into a legal map. So that is the process here, is we take something that's random and we keep moving things around until it becomes what we call a legal map. So this process is called an optimization process. And what we do is we basically give the computer the criterion and it tries to improve the map such that we get to what we call a legal map, right? And so we built an evolutionary algorithm, and the evolutionary algorithm, I don't know if you guys know about them or not, but it mimics biology. And so the idea in biology is, you have generations, and every generation it improves from the previous generation. That's the optimization, right? So every generation improves upon the previous one, and usually one of two things happens. A unit or a person, your genes are mutated, and then the person changes. Or like two units, we call them parents, they will have a child map. So somehow you take two parents and they mate and then they produce a child. And the child is supposed to be better than the parents, right? That's the idea behind the algorithm. And that's the idea behind what we call evolutionary algorithms. So that's what we built, is we built upon this type of optimization algorithm. So I'll just give you a little sense of what the algorithm does. But this, so we have a whole population of maps that we've created. And the maps are supposed to be legal maps, but they're not quite. If they become a legal map, then we save them. So the idea here is, here we have two parent maps, this A and B up at the top. And those are just two maps. And so we take two maps and we call we do what we call mating of the two maps. And so we overlap them, and these are the overlap pieces. And then what we do is we start changing chunks of this map into this map. So whatever it was in this one, we change it to what it should be in that one. And this is this process of transforming the map like that. And then this map at the end is a complete transformation. So if you look at the colors, it's that second map. It's this map and that map. But what happened in between was I was moving chunks of map over. And so the idea is if these are pretty good, what you want to do is preserve the good parts of the map. And then somewhere in between, you're hoping there's what we call a child map that is better than the parent maps. So it's a process of trying to improve the maps such that they become legal maps, as it were. And that's what we're trying to do right now, just produce one legal map. So this is just work in operations research. So these were other people's efforts to do the exact same thing, as produce this legal map. And the idea here is, I know this table is like impossible to read, but the idea is we want to get to 0. 0 is the best fitness. So the lower down you get to closer to 0, the better the map is. So among the algorithms that exist, this one was the best one. And it found a map. This number means nothing to you, but the idea is it's closer to 0 than these ones. It found this map of this quality that, again, is unimportant to you. It took it 5.3 hours to identify that map. So it started at random. It took it 5.3 hours to find a map that good. So this one, which just uses our mutation operator that I just showed you, got a better map than that. And we only took 12 minutes to do that. So this algorithm also is very bad because it found a good map at 5 hours, and we let it run another 20 hours total. It never found a better map. So it found its best map at 5 hours, and it didn't improve after that. Our algorithm found a better map at 12 minutes, and we let it run for the remainder of an hour, and it improved on top of that. This is the other operator I showed you. So when we use the two operators together, we found a better map than that map in under 2.5 minutes. So we improved the finding of a single legal map by a lot. From 5 hours to less than 2 minutes, 2.5 minutes. And then this one we also ran for the remainder of an hour, and it also got much better. So this is the process of finding one map, teaching a computer to create one map. This is a little graph of the search process. So the one operator induces a bunch of more variability and randomness, which you need, and the other one is a little bit more direct. But together, they're much better together. So this actually took a long time. And we figured out how to draw a map really quickly. But I showed you before, one map's not going to get you anywhere. It's like bringing in one apple. It's like, here's an apple. What am I going to do with one more apple? Like, I want to see lots of apples, right? And so the next piece of what we did was we enlisted the Blue Water supercomputer, which is at the University of Illinois. It was, that's a picture of Blue Waters, by the way. It's in a building that cost us $65 million just for the building. The machine itself was a grant from the National Science Foundation in the United States. It was a $350 million grant to build this machine. But the machine, it used to be one of the fastest research supercomputers in the world, but I don't know if any of you guys follow supercomputing. The whole battle is to be the fastest. So as soon as you become the fastest, somebody else is building a faster one. And there are much faster machines now, because Blue Waters is now 8 years old. 8 years old as of last week. And so it's just like your laptop. When your laptop is 8 years old, it's not very good, right? So it's the same with the supercomputer. But it was, and it's what we call a massively parallel system, which are not all supercomputers. Like quantum computers are a completely different kind of architecture. But Blue Waters is massively parallel, and it has 750,000 processor cores. So it runs at a sustained 1 quadrillion calculations per second. So it runs at peak speed, it runs at 13 quadrillion calculations per second. But it doesn't always run at peak speed. So it always runs, however, this is the sustained number. It always runs at a sustained quadrillion calculations per second. So that's basically its minimum. This is its maximum. So a supercomputer, I have a little bit trouble understanding what people think a supercomputer is. I once explained this to children, and they looked at me and said, "How big is the keyboard?" I was like, what? I'm like, they had this vision in their head that there was this giant computer along with this giant keyboard, and somehow you would jump on the keyboard to do things. I was like, that's not what a supercomputer is. But I didn't even know people were thinking that. So a supercomputer, I usually like to explain to people, if you run something like Microsoft Word on a supercomputer, it runs exactly like it runs on your laptop. Exactly the same, because it's written to run on one processor. And although the supercomputer has 750,000 processors, you're not using them, right? And so the key is how do you use these processors to make your job faster? So here, what we did was, one of the things we did was, on the supercomputer, the idea is there's a lot of processors, right? And it's a little bit like building a house. So if I were going to build a house, what I would have to do is, I have to lay the concrete, I have to do the air conditioning, I have to paint, I have to put up the drywall. I have to do everything, right? Because only I'm doing it. I'm like one processor. But if somebody else is going to help me, Dinya, for instance, she's going to help me. And then, we can go much faster because now there's two of us, right? And so, we're friends, and so we communicate pretty well, so it might work out really well. But if we weren't friends and, we didn't work together very well, I might be building the house and I might be hitting the hammer and she comes along and says, I want to hit the same nail, and then we're both hitting the nail. It's like, that's not very good, right? So even though there's two of us, if we're not working together very well, it doesn't make it faster, right? So let's say Dean Wu comes along, he says, I'm going to help too. And I'm like, okay, what are you going to do? Right? Because it doesn't matter that he just comes along. If he just comes along and he sits and he, you know, gives me lemonade every once in a while, and it's like, so the house isn't going up faster, right? He actually has to help. And then I actually have to tell him how to help, right? So there has to be some coordination between the processors. And this is the whole problem with supercomputing, is you have all these processors, and not just that you have them, how do you use them? So if I have lots of people, I can tell, you know, Dean, you have, for instance, okay, I'm going to do the concrete, and while I'm doing the concrete, you do, you know, the something else. I don't build houses, so I actually can't think of anything, but something else. And then let's say, you know, we have a really good plan going. She and I created this great plan, and the two of us are at maximum productivity for 2 people. And now all of a sudden, for whatever reason, this entire room comes over to help build the house. So I'm stuck, right? I'm like, okay, what do I do with all of you? And there has to be a plan, right? So if you all show up and you don't know what to do, or you all want to do the same thing, or we're not communicating, it's no good, right? The house isn't going to go up any faster because you don't know what to do and we're not working together. So that's how it is with the supercomputers. You get all these processors. You have to tell them all what to do, and you have to tell them which processor communicates with which processor. So the last thing I want to do, if you all want to build the house with me, is to come talk to each one of you. Okay, I go to you, okay, you're going to do this, and now your turn to have a meeting, and now I'm going to have a meeting with you, and I have to have a meeting with each of you. Or, you know, we're all working to build the house, and then, you know, at the hour, we all going to have a meeting, right, to discuss where we are in building the house. Because we have to work together to build the house. Right? And it's the same thing with the supercomputer. The processors have to work together to complete the problem. And so the other issue here is, so if I have a plan for two people, that doesn't translate to a plan for 10 people. If I have a plan for 10 people, that doesn't necessarily translate into a plan when 100 people come to build the house. And if I have a plan for 100 people to build the house that works really well, what happens when 750,000 people come to build the house? Like, it's a completely different problem, right? So it's the same thing on the supercomputer, is you have to decide which processors do what, but when you get more processors, what does your algorithm do, right? It has to be able to scale to every number of processors as you go up. So that's a big challenge. So one of the big challenges also is, what do you do with these meetings, right? So if we're building the house, every time we have a meeting, no one is doing any work. We're just having a meeting. It's just like academia. We have a meeting, nobody's doing any work. We're just having a meeting. And meetings are terrible, right? I always tell people, no, I don't want to come to the meeting because I have things to do. If I come to the meeting, I'm just sitting there. So the same thing here. When the processors are in a meeting, they're not working. Right? And so you want to minimize meeting time among processors. So one of the things we developed was this way of having these, what we call sending and receiving buffers. And the idea there is, this is exactly how I want to run a university if I ever run one day. No meetings. Like, if I want to talk to you, I just leave you a note in your receiving buffer. And when you have time, you just grab that note out of your receiving buffer and you look at it. And then you go back to work. So I don't want to have a meeting. I don't want to talk to you. And then I'm gonna put things into a sending buffer, right? I put it into this buffer. I basically send you a note, and you look at it when you have time. But we don't have to sit at a meeting. Meetings so bad, and this too. Meetings are so bad. So the idea is we developed a way to have this no meetings between the processors. That you just put things into these buffers, and that the processors could check the buffers when they need to. But they don't have to spend time stopping what they're doing to communicate with the other processors. So we tested this out on the supercomputer. And here we're using 16,000 processors, here 32,000 processors, here 65,000 processors, and here 131,000 processors on Blue Waters. And here we're just measuring how much time do you spend communicating with the other processors, and how much time do you spend working on the problem? Because all I want is you to work on the problem. And you can see it doesn't matter how many processors we use, they spend very little time in communication. So that's actually pretty hard to do. to keep communication costs low and to keep computing costs, computing high. So this is a picture which I think will mean nothing to you, but the idea here is, again, we're doubling the number of processors as we go, 32,000, 65,000, 131,000 processors. And what we want to show is that this is scalability. So as you use more processors, you want to find better things in less time. So that you want this line to go down, basically. And that is not, as I explained to you, it's not something that just happens, right? That's actually the whole process of what you're doing on the supercomputer, is figuring out how it is that when you have more processors, you can do more things in less time, instead of creating chaos, which is what you would do if you asked 750,000 people to build a house and had no plan and no way to communicate and no anything. So that's the idea behind that picture. So we are able to use the supercomputer to do that. And sometimes people ask me, why do you use a supercomputer? Okay, first of all, it's just fun. And then second of all, computers evolve really fast. So this is the Cray 2 supercomputer. It was the fastest supercomputer in the world in 1985. I don't know how many of you remember 1985. Oh, I've told this story a lot since I've been here. I've been to Taiwan once in my life. It was in 1985. I was only here for 2 days, but when I was here for those 2 days in Taiwan, the Cray 2 was the fastest supercomputer in the world, right? 25 years later, the iPhone 4 is much faster than the Cray 2. 25 years later, right? You guys are carrying the supercomputer around in your pocket and you think it's bad. You're unhappy with your supercomputer, because none of you have an iPhone 4, I'm pretty sure. That's pretty old, right? And if I gave you an iPhone 4, you'd throw it away, because you don't want to have a supercomputer in your pocket. But the iPhone 4 is much faster. And so now I think people look at Blue Waters and they think, well, who would ever use a computer like that? And I say that's going to be everyone, actually, later. And so when you have grandkids, or your kids have grandkids, they're going to look at the things that you use. My kids already do this to me. They look at the things I used when I was a kid and like, well, what is that? Like, that's a ridiculous thing. I wouldn't even turn that on. It's just not worth it to them. So it's the same thing with computers and phones in general, as they get much, much faster. So the research that we do now on supercomputers is very important, because it's not that long from now when this is like how we do everything. So the idea behind Blue Waters is, the National Science Foundation in the United States built it. But what they really wanted to do is, even when they built it, they didn't know what could be done with it. Right? And they needed science teams to go in and say, this is what we can do with that computer to justify building the next one, basically. Because otherwise they won't keep building them. Because if you build them, what can you do with them? Right? And so there's this whole question of what do you do with these machines, and actually how do you use the machines? Because if I give you 750,000 processors, what do you do with it? Right? How do you do something with it? And that's been, one of the grand challenges with supercomputing, is how do you do this? Do we actually want to keep building faster machines? Because are we actually forwarding science with that, or are we just building machines? So that's part of what this was. And on Blue Waters, I was the only social scientist that used the machine at all. In fact, the first year they came up, every year there's a Blue Waters annual report. It's really nice, because they gave us $350 million. It's really glossy, it's thick, and it has all the reports from all the science teams. And the first year when I did mine, in the introduction, they said, oh, Blue Waters has been used by all these different disciplines, chemistry, biology, astronomy, and then it had at the end, and even political science. Like, why does it say even political science? But that's what it said. And then the second year, they created an index in the annual report, and then they always ask you to look at it. So I looked at it, and then I looked at the index, and they had chemistry, and then they had a bunch of listings of projects from the chemists and biology. And then they put mine under other. I'm like, other? And I was the only one under other. And I said, what, other? And they said, what do you want? And I'm like, social science? Like, what is other? But they didn't know what to do with it. But this has been one of the challenges with the supercomputer is how do we use it? Who's using it? What justifies us building these things? So, okay, so I drew a lot of maps. So I got the supercomputer, and so first I drew one map, which was a little bit hard. Then I got the supercomputer, and I drew a whole bunch of maps, billions of them actually, with the supercomputer. But if you think about the problem again, what if I take the supercomputer or whatever, I take my super shopper and I make them get a lot of green apples. But they're only getting the green apples, right? I haven't told you that we shopped around for all the apples, right? Because it could be, the Republicans take the supercomputer and they create lots of red apples, right? So it's just like the same problem, right? You haven't solved that problem, you're just getting a lot more apples. But we could be getting a lot more green apples or a lot more red apples. What I want is not a lot more apples, actually. I want to see all the apples. And if I can't see all the apples, I want to see a representative sample of all the apples, right? And only if I have a representative sample can I justify using this as the distribution that we want to compare against. So that was the next problem. This was actually the hardest part for me because I had no idea how to do that. It just, when I thought about it, I was like, I don't have no idea how to do that. But that was the next piece of this, was how do I get a representative sample? Not just draw maps, but get a sample of the underlying set of maps. So we worked with this data set that we created, actually somebody else created. I just took it from them. But it's basically 25 precincts in the state of Florida, and we're going to separate it into 3 districts. All right? So if it's completely unconstrained, there's 10 to the 11th ways to do that, to make these combinations. It's really big. If you make them contiguous, there's only 100,000 ways to do that. And if you make them contiguous and have the same population, there's actually only 927 ways to do that, out of 10 to the 11th ways that you might have to search to find these 927 things, right? So the number of legal maps, even in this example, is pretty small compared to what you would have to search to find them. And it's not about finding them, because in a real application, we can't find them all. It's impossible. We don't have the computing power to find them all. There's too many of them. So we have to find a sample. So in this example, we can actually find them all because there's only 927. But in a real example, we can't find them all. We have to sample. But this one, since we have the answer, we can see if the algorithm works. So it's a little bit like this. If this is like your search space, that little red dot, the circle, square, is 100 times larger than all the number of things that you want to find in this space. I don't know if that makes sense to you or not. But basically, you have to search a lot of things for very few things. And you have to look around the whole thing, right, to find very few things. So, and they're not all in the center. They're just like scattered all about. And you don't know how to move around in this space. So there must be some phrase in Taiwan that's equivalent to, in the US we call it searching for a needle in the haystack. So you basically have this giant thing and you got to find something and you don't know how to find it. So the algorithm basically is, how do I move around here and find the things that I want? And it's not just finding them, it's finding all the things. If I'm not going to find all of them, I'm going to find some representative sample of them. So we used an algorithm called the Markov chain Monte Carlo, which is a pretty well-known type of algorithm. But the idea is, I don't know how much you guys know about Markov. We call it MC. But the idea is, if you just move around like in a little space, like you move around a little bit, that kind of Markov chain is fluid, meaning it will move, but then you're not moving very far, and it would take literally forever. More computing time than you have to move around this entire space. So you can't make little changes to a map. You can make little changes to a map, but if you only make little changes to find the next map, it's really hard to figure out where the maps are coming from or where to move for the next map. So if you make large random changes in your Markov chain, then you can move, like, let's say you found a good map here. Now you're going to move somewhere else in the space. Well, how do you know where to go? So if you just make a large move, almost certainly you move somewhere where there is no map to be found. And so then you're just wasting computing time. So we need some intelligent way to search this space, some way to move around in an intelligent fashion, like I know where to go, I have a good idea of where to go next. And so that was the challenge behind this. So we developed what we call an evolutionary spatial sampler. And the idea is that I have to search around in this space, but I don't know where to go. And if I just move around at random, I go nowhere all the time. Basically, almost all the time, I'm wasting computing time, and I go nowhere. So we took what we had built first, which was this optimization routine that creates a good map, and we said, okay, that routine will guide the Markov chain. And that will improve the sampling. It'll make the sampling faster. It'll teach us how to make a big step versus a little step in the map. So if you just use an optimization step to choose the next map, that works, except it's not random. And it will not satisfy the properties of an MCMC algorithm, and then it won't produce a sample. Then you're just creating maps again. You're not creating a sample. So what we did was we combined these two ideas of sampling and optimization into what we call a multiple tri-metropolis Hastings model. So metropolis Hastings model in MCMC basically says, I found something, should it be in the sample? And then this metropolis Hastings ratio is this probabilistic thing where it says with this probability it'll go in the sample, with this probability it won't go in the sample. And if you compute that metropolis Hastings things right, the theory of MCMC, the mathematical theory behind that method, will produce a sample for you. So we're making steps. That's if you're moving around in some acceptable random fashion. And we are not, because if we move around randomly, we get nowhere. So we use this optimization routine to tell us how to move. And then if we use that optimization routine, we're no longer random. So that's the problem, right? So what we did was we used the optimization routine to draw what we call trial proposals. So the optimization routine goes searching around and it says, go in this direction. Here's another good direction to go. It proposes several different ways to go. And then you have to work on a little bit of math to figure out what then is the probability that I should accept or reject a certain proposal. So that's what this was. So this idea of how to do this is what took me forever, actually. This was the longest part of the project for me. But we adapted, the first thing we had, which was our mutation. That one actually adapts really easily to this format, because this piece, you hope, actually just drops out, becomes the same and drops out. It cancels, but it doesn't cancel the way we did it. But you can compute this piece combinatorially with a computer. It's actually just searches, and then you search all the ways in which it can change, and then you can compute both of those probabilities. This is the crossover, which was the two parents that mate and create a child. That one was a lot harder, because that one is really a non-random type of movement. But we basically figured out how to do it, and that also became a combinatorial search by the computer, searching through, finding all the ways that something can be done. So it's using probability, and it's using a computer to actually count all the ways that something can be done, and then that becomes the probability. So there's a lot of computing going on there. It turns out if you just use what we call an ordinary Monte Carlo, that doesn't work. So different people have proposed, you can do this, you can do that, but it doesn't work. So for instance, this one by Chen and Rodden, this gray distribution for the example I showed you is the one we're trying to recreate. You're trying to draw a bunch of samples and then recreate this distribution. So it turns out if you use their algorithm, you get this red distribution. So this is actually exactly like this idea where that's not the distribution. And if you use this algorithm and you create this thing, then later when they want to know, a map that's here, which would be a perfectly typical map, this algorithm would say that map is excessively partisan, right? Because it drew this distribution instead of this gray one, right? Or this other algorithm draws this other distribution. Those are just way off, and they should never be used for judging things. Because for this, you don't want these distributions that are not the real distribution. They're just wrong, right? And they cannot be used at all. It doesn't matter that you produce the distribution or you produce this shape it's kind of like coming in with the apples. It's like it's a biased set of apples, right? And we can't have that. So it turns out if you don't devise your MC right, it does the same thing. You know, this distribution is the one we're trying to recreate, and it doesn't work. It doesn't work. So there's a whole, you know, I wrote several papers on this because people keep saying, oh, I have one. I'm like, well, that one doesn't work. And then you have to explain to people why it doesn't work. But a lot of these things, you know, they don't work. So this one is ours, what I call the evolutionary MC. So this one is, the red distribution is the one we want to recreate. And I know these colors don't look right. In fact, they look terrible to me at the moment. But this color is different than this one. This is supposed to be blue. The blue one is what our algorithm came up with. And then this purple here is the overlap. And so we did this with one processor core, 16 parallel Markov chains, 5 seconds of compute time, visiting approximately 7,000 steps in 5 seconds each chain. And we reproduce the distribution, basically, is what I'm trying to show you. That this is the 927 solutions. And we visited thousands of them, but we visit them in the right proportion, right? It's the right proportion. It's the right distribution that results from that visit of the different maps. So this is also our algorithm, scaling on 2,000, 4,000, 8,000 processors, finding a lot more solutions, like more than double the number of solutions as you double the number of processors. So the idea there is the same thing that I was explaining to you before, that the algorithm scales with processor cores. So, you know, just because I have twice as many now, it doesn't slow it down, it makes it faster. And then that was the little application with 25 precincts, 3 districts. This one is 10,000 spatial units partitioned into 16 units. And so here we went up to 16,000 processors with 4 hours of runtime on Blue Waters. And also here using a lot more constraints on what the maps are supposed to look like. And so we were able to create millions of maps in that about 4 hours of compute time on a very large application. All right, so that's the massively parallel version. Now here comes the social science. So we developed all this technology, and there's been a lot of talk in the redistricting community about what you're supposed to do with this type of thing. And the main discussion has been that in the last 30 years or so, we've been developing software and technology for redistricting. And in the last 30 years, what happens is the politicians have been using it to draw better and better gerrymanders. Like they go, oh, now I can keep track of where all the people are and where all the people move, and now I can make even a better map than I was making before because I didn't have all this information before. And so the use of this software is pretty hard because it's actually hard to draw these maps, and it's hard to know how to manipulate them to get the outcome you want. And you actually have to be pretty, good at, what it is you're manipulating. So in the last 30 years, basically, the politicians had been drawing better and better gerrymanders. And we're at this point in the United States where we're like, this has got to stop, right? We're creating software, and we're making everything worse. So in, I believe this case was 2018, Whitford v. Gill, the Justice Elena Kagan, who's on the US Supreme Court, said that the 2010 redistricting cycle was basically the worst we've ever seen in the United States. We've never had such skewed maps ever. And then so many lawsuits of people saying, this map has to be overturned. And she said, the technology is getting better. So this next time in 2020 when we redistrict, this is going to be even worse than the last time, right? And she's basically saying, what are we doing? Like, why are we developing this technology to make us so much worse? I'll talk you through this. This was a video that Vox made for us a couple years ago, but they're basically talking through our algorithm, and they're talking about partisan gerrymandering and how it's gotten worse and worse. And there I am. This looks just like me? No, maybe. And here is my co-author, Yen Liu. But they were talking about how we used a supercomputer, and then we're trying to build what I'd explained to you is this gerrymandering ruler, right? Some way to actually have a systematic way of measuring it. So here they're saying when you redistrict, there's lots of things that you can do. You can create lots of different shapes. And then how do you figure out what is what? So what you're trying to do is you're trying to figure out the person who drew the map, what are they thinking, right? And the court doesn't know how to figure that out. But if they use partisanship too much, that's bad. So these are the criteria that you can actually use. Make the population the same, for instance. Make this contiguous. So this is where I told them this thing about the maps connecting underwater. And then these other ideas about how you would connect people. So this is also just kind of general map drawing things. So I said we use the supercomputer. I love this part. He created this nice video for me. I gave him these maps and he moved them up and down like this. I thought it was great because this is not what we look at. We just literally look at a screen with code on it. But I thought this was a really nice visualization. And the idea here is, you're looking through all these maps. And if you look at all these maps, and the ones without partisan bias create a completely different partisan balance in the maps than the one you're looking at, then maybe you should overturn that map, the Supreme Court. So I like that. I like that visual. I love that visual, actually. So I'm going to stop that thing. But the idea was, I have another funny story. One time this reporter called me and asked if he could come videotape me working. I said, that's really boring. I'm like, what are you going to tape? And I think he had this idea that my computer looks like this with all these maps lying all over. It's like, I don't do that. I said, so I'm going to sit in front of a computer, and then how long are you going to have me videoed? Because it's really boring. Anyway, I convinced him not to come. But I think that was the idea, that he thought that, I see these things, but I don't see them. I just run code, and the code runs, and you don't get all these visuals. But that video, I think, helps people understand things better. So that was the video without sound. But 2 years ago, in 2019, I was an expert witness in this case for the state of Ohio in the United States. So the state of Ohio was being sued by the Democrats because the Republicans had drawn the map in 2010. And there's 16 congressional districts in the state of Ohio, and 12 of them are Republican. And in every 2 years that they had voted for congressional members, it was always 12. So in 2012, they had an election, 12 Republicans, 4 Democrats. And then 2014, they had an election, same thing, 12 Republicans, 4 Democrats. So every 2 years, it created the same thing. And the Democrats sued, and the state of Ohio is about 51-49 Republican Democrat. So it's just barely more Republicans than Democrats. But the Republicans were carrying 75% of the seats. So that was just kind of like the situation I showed you earlier. So we took the supercomputer. I was the expert witness. And I took the state of Ohio, and I drew 3 million samples of the maps that could be drawn in the state of Ohio. We actually drew, so this is another thing I always say about this, we actually drew 3 billion maps. But when you have a supercomputer and you're getting so much output, it's actually really hard to deal with the output just coming out. It's not just you can do it. Once you do it and you get the things out, you have to do something else with the output, right? And so I couldn't handle that much output. There was too much output. And so I sampled it down to 3 million. So the sample itself was actually much bigger. But we tried to explain it to the judges in this way, where I've drawn this distribution, and if it's an unusual outcome, then the judge, you can toss that out because it's excessively partisan, or it's a very strange outcome given what you think should happen in a fair process, right? So we explained it to them with coin tossing. That the idea that if you have 100 tosses of a fair coin, most of the time you should get 50, but if you get 55, that's not really weird. If you get 60, that's a little bit weird. The judge gets to decide how weird is weird. If you get 70, I don't know if this is unusual to you, but 70 heads is almost never when you toss a coin 100 times. So if you don't draw this for people, you don't produce this actual distribution, people actually don't have any idea what's unusual and what's not unusual. And it's the same with these maps. You don't actually have an idea what's unusual and what's not until you produce the distribution. So this was the distribution we produced for them. This is House Bill 369, which was the redistricting bill that drew the maps. And they had 12 Republican seats. So then I drew them with the computer, and this was my distribution of seats. That most of the time you should get about 9. You should get 9. 8's not unusual, 10's not unusual, even 11, you know, but 12, and you can't actually see this on this histogram, but the computer, out of the 3 million that I produced, there's actually 1,400 something maps that are here. But that's such a small proportion of this histogram that it looks like there's nothing there. There actually is 1,400 maps over here. But the idea was we were trying to explain to the judge, that's super unusual. It can happen, but it doesn't really happen. So we also produced this map, which took the same maps and it said, okay, how many of the seats in the state of Ohio should be competitive? Like should be a somewhat close election instead of a very, you know, instead of a very safe seat where it doesn't matter who runs, like the Republican will always win because there's so many more Republicans than Democrats. So this was how many of the seats should be within a 10% margin of victory. And we came up with this 8 or 9 basically. And in the state of Ohio for the map that they were actually using for Congress, it was 0. So they had no competitive seats, which is why every time they had an election, it was 12 Republicans and 4 Democrats, because none of the seats were actually up for election. I mean, they were all up for election, but none of them were competitive at all. So getting to the role of AI in democratic governance. So in the United States, this is just recent. The US Supreme Court in 2019, so just 2 years ago, said partisan gerrymandering is non-justiciable, meaning they can't hear these cases. They will not hear these cases, the Supreme Court in the United States. And so the problem for them was they didn't understand how they could decide, right? And it's the same thing I was explaining to you. If you just give them a map, they look at the map and they're like, yeah, sure, the Republicans drew it, they drew it for themselves. Of course, but I'm a judge, right? I can't just say, yeah, I think so too. It's like when you know, if you're being on trial for murder, you don't want the judge to look at you and say, yeah, you look like you committed murder, right? There has to be a rule. There has to be something very, you know, standard that they use and that they always use for everyone and for all maps. So this was the same idea. They couldn't understand how to do it besides, I don't like it. Right? It looks like it would be bad. Seems obvious to me. That cannot be the legal rule. And they couldn't think of a legal rule. We explained this one to them, but they didn't understand it. They asked questions, but they didn't understand it. They had this, Justice Samuel Alito said at the Supreme Court hearing, so you drew these maps, and basically the one I showed you, so some of them had, you know, 12 Republican seats with your computer that wasn't trying to do this. It's like, well, the answer is yes, right? Because that happens. It's just like when you toss a coin, sometimes you get 70 heads. Sometimes you get 90 heads. It can happen, but it's unusual. It's not supposed to happen, right? And if it does happen, then you would say, if I gave you a coin and you got 80 heads, then you should say, that's not a fair coin. It might be a fair coin. But if you got 80 heads, you should say it's not a fair coin. And it was the same thing we were trying to explain to the Supreme Court. When you get these outcomes that are so unusual, they probably were cheating, right? And they thought, oh, well, but it's still a fair coin. Like, I didn't understand that. But they didn't understand. They didn't understand what we were doing. We didn't understand what they didn't understand. A little bit of a communication issue. But they had to rule on this, and they ruled that it was non-justiciable. So you can actually still sue in state court, which is a different system than the federal court in the United States, but you can no longer take your case up to the Supreme Court. So then that leaves this question of, you know, what is the role of technology moving forward? You know, we create all of these things. It's for, you know, social progress. You know, what are we supposed to do? So one of the things they did actually after that was, you know, in the state of North Carolina, they had this great idea. You know, the computers draw maps. They're better than the humans. Let's just replace the humans. Let's just use a machine. So they produced a bunch of maps by machine, and they actually put numbers on the maps, and they put the numbers in a lottery machine, and then they ran the lottery machine, and then out came a ball. They said, that's your map. They actually did that. That's so stupid. And the reason that doesn't work is humans are not machines, but machines are not human. And this problem of redistricting, what people aren't understanding is it's a very complex socio-political issue. And the role of technology is completely non-obvious here, right? And so I think a lot of times, especially these days, people do things with computers and people say, wow. Or, you know, you use a supercomputer, people say, wow. It's not really wow. It's a different question. The one they want to answer is a different question, right? And what you want to do with a computer is not make philosophical or political judgments about what it means to fairly represent a society in Congress, right? So in the United States, you know, what is fair? That's not a computer question. It's a human question, right? It's like, should we produce a representative for a minority group if they are 20% of the population? Should we produce one? Should we produce two? What if I give the minorities a representative and it takes away from something else? Because it always takes away from something else, right? Is that fair? Like what is fair? And there's so many groups. It's like there's racial groups, there's women, there's, you know, sexual orientation. There's all sorts of things that you want represented, right? And this idea of how many for each one is a very, very complex issue. And it is not a technological issue. It's an issue for humans to decide on fairness. Right? So these debates over philosophical values and how you should represent society, or even, you know, how many legislators, how should they be divided, what are the rules for institutions, those are philosophical debates. Those are political debates. It's not a mathematical exercise. So this idea that we could take redistricting and just turn it into this, it doesn't make sense, because these things that were drawn by computer didn't consider all the things that a human would consider. Right? And so one of the ways I like to explain this is, you know, this idea that what is easy for humans is actually very hard for machines. So you see this all the time, right? When you're on a computer, find this, right? Find the palm trees, find the traffic lights, and you're like, click, 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 click. Right away, you can do it, right? A computer, very hard, super hard for a computer to do, right? And that's why it's trying to figure out, you know, are you human, are you a computer? And it's the same thing with these things we call CAPTCHAs, right? A computer, to figure out what those letters are, super hard, but a human, just like that, right? No work whatsoever. On the other hand, what's easy for machines is very hard for humans. So this is a picture of Big Blue in 1991, I believe. 1990. 97? Oh, 91 was the first time he beat Big Blue. He beat Big Blue, and then he lost to Big Blue. This is the one where he lost to Big Blue. So that's Garry Kasparov, and he's playing, and he loses to a machine, right? And the idea was, for a long time, we didn't know if that would happen or not. But the machine here is doing so much more calculation than the human. So machines have this thing that they can do, and then humans have this other thing they can do. But what machines and humans can do is completely different. So I always say that the algorithms we wrote, even though it took us like, 8 years basically to do it, which is a pretty long time, it's actually very easy compared to this idea of ensuring political fairness for a richly diverse society, right? This problem is like super hard. And it's super hard for humans to decide on what that even is. So I always say the easy problems are in math and computer science. The hard problems are actually in the social sciences. Right? The social scientists have all the hard problems. The computer scientists, they have all the easy problems. They're straightforward, they're, have a lot of structure, they have a lot of form, right? But the social sciences, you ask them to do this, like, I don't know how to do that. How do we make sure this is fair? I'm like, what does that even mean? Like, how do I decide on fair? How do I decide on, there are all these constructs that are completely unclear. Whereas math and computer science, piece of cake. Right? You have to spend some more time, you think a little bit more, but the problem is so well defined for these other disciplines. And for the social sciences, solving that problem is really hard. So if we compute more, that doesn't mean it's more fair, right? I did a lot of computation, a lot. Does it make it more fair? No. Did I do more computation? Yes, right? More computation means I can find more patterns in data. Is that more fair? No. Did I find more patterns? Yes, I did find more patterns. And this is an important point that I think people don't understand is even though you do more computation, it actually has no relationship with the moral and ethical standards by which you want to judge or run an evolving society, right? In society, even though you make a rule at one point that might be fair, society evolves. And then all of a sudden, it's a different problem, right? And you can no longer keep using that rule. And this idea of morals and ethics and population, people change, and we've seen this change over time. This idea that 20 years ago, what we thought of, say, sexual orientation and whether or not we cared about it or wanted to represent it, completely different than now, right? And now we're moving into this other place where it's not just sexual orientation. Now gender has become binary, non-binary, and it's like, who saw that coming, right? Because 30 years ago, if you told somebody that, they're like, well, what are you talking about? And now it's like this big part of conversation. And 30 years from now, we're going to be discussing something else that also we didn't see coming. Right? It's like, what? That happens in society? What society? And society is constantly evolving this way. So this idea that you can just compute more, it's a completely separate thing. I can compute. That's great. That's great. That's it. Right? So sometimes I like to show this this trolley problem. I think you guys all know this trolley problem. It's pretty famous. But the idea is, the trolley is coming down the road, and here it has to, to veer off, so it can either kill this one person or it can kill these 5 people, but somebody is going to die. How is that decision made? Should it be made by a computer? Should it be made by, and even for a human, this is such a complex problem, right? Because there's so many things to decide. Who are these people? Are some old and some young? Is it really 1 is less than 5? You guys know the trolley problem. It's a very complex, a very, philosophical problem about the value of human life and what should be valued and what should not be valued. So a computer can make this decision randomly, but random is not fair, right? But it is random. And if it's not purposely unfair, which is what a computer is, a computer is not purposely unfair, right? But that doesn't make it fair, right? So this other time when in North Carolina they decided to use this machine and they say, okay, you humans, you guys are always unfair, so we'll use a computer, it's not purposely unfair. Like, okay, it's not purposely unfair, but that doesn't make it fair, right? And people don't understand this idea. And so, machines, they can produce information, they can produce a lot of things, but it's the humans that have to infuse the values into these decisions. It's the humans that have to decide, what is it that we're trying to do with these machines. So ensuring representational fairness is which is what we're trying to do with redistricting, requires metacognition, right? And there has to be humans involved to think about what are the benevolent compromises here, because there have to be compromises. There have to be compromises, right? And that's a human decision. It's not a machine decision. But a machine can say, okay, here are the trade-offs. If you give this, then you take that. If you do this, then you do that, right? But a computer cannot make those decisions. It's just like a computer should not be making this decision, right? And this is a debate now in, with autonomous vehicles, right? So you have an autonomous vehicle, and there's going to be an accident. Which accident should happen? One person dies, this person dies. It's random. Dude, is that what we're looking for? It's like, but it's random, right? So I always have been saying this for a little while, that the way forward is for people to work with machines to produce things that we couldn't produce before we had the machines do this. That we have to capitalize on both artificial intelligence and human intelligence, and to understand that those are very different things, and to use them in the ways in which you capitalize on the strength and minimize the weakness of both. So machines can produce lots of numbers, lots of computation. Humans can think. Humans have metacognition. Humans know why we are doing it. The machine has no idea why. So the role of AI, I think, is for the machines to create these to work with humans, that they can look at all the possibilities for electoral maps. And then the humans, they have to deliberate, right? And that this process has to iterate. It can't just be the machines do something and the humans are like, okay, machine's done, let's do that. The humans have to think a little bit. And it can also produce public information, because this is another problem that we've had with redistricting in the United States, is the politicians draw a map and then they pass it, and then everybody else doesn't know what to think about that map because there's no information, right? They just say, you ask them, was this fair? And yeah, it was fair. You know, it was not fair, but you have no information, right? So if you have machines that can do this, then this will change the whole process, and it will be the impetus for reform. And it will also help us to understand you know, democracy better. What does it mean? What do you have to trade off? What does it mean to represent something fairly? You can use new information to study things like that. So the idea is, you know, automation, it really can't replace human labor. What it can do is it can improve human labor, and this is what we want. But we need the humans to use it to produce something productive, something where we include people, and something where we're actually thinking about new information. So last one. So AI is a tool, right? It's a tool. And humans have to choose to use the tools for good. Because right now, what you see is people can create these really complex tools, and then the humans, they don't use them for good. They just use what they want for what they want. And that's a human problem, that humans are not using these tools for good. But the AI tool is really no different than like a hammer. We created a hammer, right? That's a tool. So it's like, okay, great, we created a tool. It's a hammer. A hammer is super useful. A really great hammer. So we can also use the hammer to hit each other. Then it's a bad tool, right? Because what am I doing with the hammer? I'm killing people. I'm going to just hit people. And that's bad. So if people use tools to harm, the humans have to decide how to regulate their usage. Right? The humans have to look at the tools and say, how do I regulate the usage of this kind of tool if people are going to use it for good or bad? Because it doesn't matter what you create, some people use it for bad, right? And some people use it for good. And somehow we have to, as a society, figure out how to regulate these types of tools. So we can use a hammer to build houses to take care of each other. And it's the same thing with all the tools. We can use them for good, or we can use them for bad. And one of the things with my tool that I built was, at the beginning I was thinking, oh, after I build this, then, you know, I can make it open source or something. Other people can build on it, and then, you know, we can use it to do something good. And then I met some of these other people, and they wanted to use it for bad, basically. And you can use what I built for bad. It's basically using technology to manipulate further and further how these maps are drawn. And now you can do that even better. And then I decided nobody can have it. So now it's just mine. Because it just, I didn't even see that problem actually when I started working on it, that how it could be used for bad. And I think this is true of a lot of technology today, social media, you know, all the things that these people are creating. We don't know what it's doing to society because nobody is thinking before they're built, right? And once they're built, they're there. And then what happens to them is a human issue, right? And we're not spending enough time on that. And that is really hard, which I've been trying to explain to people. This thing with AI, computer scientists, easy. It's actually easy. And it will move forward. It is moving forward. It will move forward. But the hard problem, we're not spending enough time on. The hard problem of the social scientists, what are we going to do with this? How do we regulate before things are created? Nobody is spending time on that, or not enough people. And the people spending time on that, they don't understand the tools, actually. So that's the whole talk. Thank you.